A star that convinced astronomers it might have an alien megastructure 10 years ago just got a real answer this July, and it's stranger than anyone expected. This is the actual state of James Webb's biggest unsolved puzzles right now. No fabrication, no guesswork dressed up as fact, just what the telescope has genuinely found and what scientists still can't fully explain. Back in 2015, a citizen science project called Planet Hunters flagged something strange in data from NASA's Kepler telescope. A star called KICE 84628552, now better known as Tabby's star, named after astronomer Tabitha Boyajian, was dimming in ways nobody had ever seen before. Not a small, steady dip like a planet passing in front of it, but sudden irregular drops in brightness, sometimes losing over 20% of its light for days at a time, with no repeating pattern anyone could pin down. Normal planets don't block that much light. Nothing in the textbooks explained it. Within months, the idea that got the most attention, half seriously and half as a thought experiment, was that astronomers might be looking at a Dyson swarm, a hypothetical structure an advanced civilization could build around a star to harvest its energy. The Breakthrough Listen project actually pointed the Green Bank radio telescope at the star to check for artificial signals. They found nothing. Over the following years, most astronomers landed on a more down-to-earth explanation. Clouds of comet fragments or dust, breaking apart as they swing close to the star and passing in front of it at irregular intervals. That fit some of the data, but it never fit all of it. The long-term dimming pattern, where the star had apparently been getting fainter for over a century according to old photographic plates, was harder to explain with comets alone. The mystery never fully closed, it just got quieter. Along the way, researchers tried other angles too. Studies comparing how the dimming looked at different wavelengths of light found that the fading was more pronounced in ultraviolet light than in infrared, a pattern that pointed towards small dust grains rather than any solid, opaque structure, since a genuinely large object would block light more or less evenly across every wavelength. That finding effectively ruled out the more dramatic megastructure idea, for at least the long-term dimming, even as it left the sharper, shorter dips only partly explained. Other teams tried fitting the light curve with models built around a family of dozens, sometimes over 100, individual comet-like bodies passing in tight formation. And while those models could roughly reproduce some of the dips, they required oddly specific and, in places, physically strained assumptions to work. A few researchers proposed a large planet with an extensive ring system, similar to a scaled-up version of Saturn's rings, passing in front of the star roughly once every few years, which could account for some of the deeper, more structured dips. None of these models fully closed the case on their own, and none of them ruled out the others outright, which is part of why the mystery dragged on for a full decade without a clean resolution. Then, this July, a team led by astronomer Flavian Kiefer and colleagues published new findings that reopened the case in a genuinely exciting way. Digging through data from NASA's TESS satellite, the successor to Kepler, they found something nobody had caught before. A single, long, smooth, symmetrical transit lasting about 21 hours, cutting the star's brightness by just over 1%. Unlike the ragged, asymmetrical dips that comet dust tends to produce, this dip was clean and round, the kind of shape you'd expect from an actual solid object passing in front of the star, rather than a loose cloud of debris. Combined with years of radial velocity measurements, tiny wobbles in the star's light caused by the gravitational tug of something orbiting it, the team calculated that Tabby's star likely has a large companion, somewhere between 9 and 28 times the mass of Jupiter, sitting in the fuzzy zone between a giant planet and a failed star called a brown dwarf. It's a tentative detection, backed by a signal strong enough to take seriously, but not yet strong enough to call proven, and the same team has already mapped out several future dates when a repeat transit could confirm it for good, with a promising window opening in October of this year. The researchers also tested and largely ruled out the more mundane alternative explanations for this particular signal. They checked whether the transit could be caused by a small companion star eclipsing a faint, previously known red dwarf that sits nearby in the same system, but the shape of the dip didn't match what an eclipsing binary star pair should produce. And there was no sign of the second eclipse that a genuine binary system should show every orbit. They also tested whether this new transit could simply be one more irregular dust event like the ones Kepler originally found. But the unusually clean, symmetrical shape argued against that too, since real dust clouds tend to produce lopsided, uneven dips rather than a smooth, round one. Piece by piece, the more exotic and the more mundane explanations both got weaker, leaving the giant planet or brown dwarf companion as the best remaining fit for what the data actually shows. Here's why this matters beyond just settling one celebrity star's decade-old mystery. If a real companion is out there, its gravity could be exactly what's been dragging in and shredding those comet-like bodies for years, scattering them into star-grazing orbits that produce the irregular dimming Kepler first caught. In other words, The actual answer might turn out to be two mysteries solving each other, a hidden planet stirring up a debris field, rather than one wild explanation on its own. Nobody involved in this research is talking about megastructures anymore. This is real patient science, closing in on an answer a full decade after the question first went viral, and doing it not with speculation, but with a repeatable, testable orbital model that astronomers can go back and check against the sky in a few months. While Tabby's star has been keeping astronomers busy close to home on a cosmic scale, Webb has been running into a much bigger, much stranger problem out at the edge of observable time. Since its very first deep field images, the telescope has kept finding galaxies that, according to standard models of how the universe grew after the Big Bang, simply shouldn't exist yet. Astronomers have started calling this the impossible galaxies problem, and it's one of the most actively debated puzzles in cosmology right now. Here's the shape of the issue. Under the widely accepted model of cosmic history, matter in the very early universe should have needed a long time, hundreds of millions of years at minimum, to clump together under gravity, form the first stars, and slowly build up into full galaxies with real structure. Webb, using its ability to see extremely faint, extremely distant infrared light, has instead found galaxies that appear fully formed, unexpectedly massive, and in some cases already organized into spiral shapes, at a point when the universe was only a few 100 million years old, a small sliver of its current age of nearly 14 billion years. One particularly striking example, nicknamed the Big Wheel by the team that found it in 2025, is a massive spiral galaxy that existed within the first 2 billion years of cosmic history. Spiral structure is supposed to be something galaxies develop gradually, after settling down over billions of years. Finding one that early caught astronomers off guard. It's not an isolated case either. Researchers have documented a real excess of unusually bright, massive galaxies at these extreme distances compared to what standard models predict, along with active galactic collisions happening far earlier than expected, and supermassive black holes already sitting at the centers of galaxies within the universe's first billion years, when there simply shouldn't have been enough time for black holes to grow that large through ordinary processes. Just this past July, a separate team offered one possible piece of the puzzle for that last part, suggesting some of these apparently oversized black holes might actually be smaller ones, growing at extreme, almost unphysically fast rates, throwing off so much radiation that they get mistaken for giants. That's a good example of how this story usually goes. Not every impossible-looking object turns out to be equally impossible once astronomers dig deeper, but plenty of the puzzle remains genuinely unresolved and nobody in the field is pretending otherwise. There's no single agreed-upon fix yet. Some researchers think galaxies in the early universe formed stars far more efficiently than current models assume, converting raw gas into stars unusually fast in short, intense bursts. Others suspect the earliest generations of stars may have skewed toward being more massive on average than stars formed today, which would make young galaxies look brighter and more developed than their actual age would suggest. A smaller number of researchers have raised the possibility that something about the standard cosmological model itself may need adjusting, though that remains a minority position and is far from settled. What's genuinely rare here is the scale of the disagreement. This isn't a fringe debate at the edges of astrophysics. It's a mainstream, actively unresolved argument happening in peer-reviewed journals right now, and Webb keeps finding more of these overachieving early galaxies every observing cycle, which means the puzzle keeps getting bigger rather than resolving itself. Adding to the strangeness, in January of this year, a team at Texas A&M announced the discovery of a tightly packed group of galaxies actively colliding and interacting with each other in the early universe, a system researchers nicknamed the JWST Quintet, surrounded by a halo of oxygen-rich gas that itself hints at a surprisingly advanced level of chemical enrichment for such an early cosmic era. Galaxy collisions like this were expected to become common only much later in cosmic history, once galaxies had enough time to grow large enough and drift close enough together to actually interact. Finding a cluster of them crashing together this early adds yet another data point to the growing pile of evidence that whatever built the early universe's structure, it moved a lot faster than the standard timeline predicted. Taken together, the impossible galaxies problem isn't a single strange object anymore. It's becoming a pattern spanning galaxy shapes, galaxy masses, galaxy collisions, and supermassive black holes, all pointing in the same uncomfortable direction. Something about the first billion years of cosmic history happened faster, or differently, than the textbooks currently describe, and nobody has fully worked out why yet. Closer to home, Webb has also been quietly rewriting what we thought we knew about a planet most people haven't thought about since a school science project, Neptune. Back in 1989, Voyager 2 flew past Neptune and gave humanity its only up-close look at the planet's atmosphere, recording a baseline temperature that stood as the reference point for decades. When Webb turned its instruments toward Neptune, scientists expected some change, since the planet's extremely long orbit means its seasons last decades and its atmosphere shifts slowly over time. What they found instead was far more dramatic than ordinary seasonal drift. Neptune's upper atmosphere had cooled by several hundred degrees since Voyager's flyby, with researchers describing the 2023 reading as sitting at just over half the temperature recorded back in 1989. One of the lead scientists on the study, Dr. Henrik Mielin, said he was genuinely astonished by how cold the planet had become. That cooling turned out to explain a separate long-standing mystery. Nobody had ever been able to photograph Neptune's auroras before, despite strong theoretical reasons to expect them, similar to the shimmering polar lights on Earth, Jupiter, and Saturn. It turns out the atmosphere had simply grown too cold and too faint for older instruments to pick up the signal. Once Webb's infrared sensitivity was pointed at the planet, the auroras showed up clearly for the first time in history, hiding in plain sight for over 3 decades simply because nothing built before Webb was sensitive enough to catch them. The bigger mystery is why Neptune cooled so much in the first place. A widely cited 2022 study using 20 years of ground-based data had already flagged this unexpected cooling trend before Webb even confirmed it directly, and scientists have floated a few possible explanations without settling on one. It could be tied to Neptune's roughly 11-year response to the Sun's own solar activity cycle, since researchers have found a tentative, not yet fully confirmed, correlation between solar activity, Neptune's stratospheric temperature, and the number of bright clouds visible in its atmosphere. It could also be connected to slow seasonal shifts in the planet's atmospheric chemistry, changing how efficiently heat escapes to space, or it might simply be natural, hard-to-predict variability in Neptune's weather patterns that nobody has enough long-term data to fully model yet. Scientists studying the planet have been honest that they don't have a confirmed answer, and that resolving it will require years of continued observation, exactly the kind of patient, ongoing work Webb is now positioned to provide. From a cold, slowly changing gas giant in our own solar system, Webb's other major frontier has been much warmer territory, the search for atmospheres and potentially habitable conditions on rocky planets orbiting other stars. The most closely watched target for this work is the TRAPPIST-1 system, located about 40 light-years from Earth, home to 7 roughly Earth-sized rocky planets, several of which orbit in the zone where liquid water could theoretically exist on a planet's surface. Because the system's small, cool star makes these planets unusually easy to study. Compared to planets around Sun-like stars, TRAPPIST-1 has become one of the single most important test cases for figuring out whether small, rocky, potentially habitable worlds actually hold onto atmospheres at all. The early results have been a genuine mix of disappointment and cautious hope, which is exactly what real science tends to look like. For TRAPPIST-1b, the innermost planet, Webb's observations conclusively ruled out a thick, hydrogen-rich atmosphere and found readings most consistent with a bare, airless rock, similar to Mercury, with little to no heat being carried from its blazing day side to its frozen night side. That was already a meaningful result, since it directly tested and rejected one of several competing predictions. TRAPPIST-1c produced a similarly ambiguous picture, with data that couldn't yet distinguish between a bare rock and a planet with a thin atmosphere. Follow-up work on TRAPPIST-1d has placed increasingly strict limits on what kind of atmosphere, if any, that planet could be hiding. The planet everyone's most interested in is TRAPPIST-1e, sitting arguably the closest to Earth-like conditions in the system's habitable zone. Here, the picture has genuinely started shifting towards something more hopeful. Researchers analyzing Webb's transmission spectroscopy data on TRAPPIST-1e have already ruled out a puffy, hydrogen-dominated primordial atmosphere and a handful of specific gas combinations. But they've found the data still allows for the real possibility of a denser, nitrogen-rich secondary atmosphere, the kind of atmosphere that could plausibly support liquid water rather than instantly stripping it away. As of this year, a dedicated follow-up campaign is roughly halfway through, observing 15 additional transits of the planet specifically to nail this down, with the team leading that effort saying they expect to finish gathering data by the end of this year, and full results are expected to be published sometime in 2026. Webb has also already begun similar atmospheric searches on TRAPPIST-1f, G, and H, the outer 3 planets in the system, with those results expected within the coming year as well. Studying a small, rocky planet's atmosphere from 40 light-years away is an enormously delicate task, and TRAPPIST-1's own star makes it harder than it might sound. Because the star is small, cool, and prone to flares and star spots, its own surface activity can bleed into the light measurements and mimic or mask the faint signals scientists are actually looking for. Astronomers have had to develop increasingly careful statistical techniques just to separate genuine atmospheric signals from the noise created by the star's own restless surface, and several early claims about the inner planets had to be revisited once researchers realized how much stellar activity was contaminating the data. That's part of why progress here has felt slow and cautious compared to some of Webb's flashier headlines. The team isn't chasing a quick, dramatic announcement. They're trying to get an answer that will actually hold up once other researchers double-check the numbers. None of this amounts to a confirmed discovery of a habitable world, and none of the scientists involved are claiming that it does. What it does represent is real, incremental progress on one of the hardest technical challenges in modern astronomy. Trying to detect and characterize the faint atmospheric signature of a small, rocky planet 40 light-years away, using starlight that has to pass through or reflect off that atmosphere on its way to a telescope sitting 1,000,000 miles from Earth. Every ruled-out scenario narrows the possibilities. Every planet that turns out to be a bare rock tells scientists something important about how atmospheres survive, or fail to survive, around small, active, frequently flaring stars like TRAPPIST-1s. Put all of this together, and what you get isn't a single dramatic headline, but something arguably more interesting. A telescope that keeps running directly into the limits of what scientists thought they understood, in completely different corners of the universe at the same time. A star that spent a decade as an internet mystery might finally have a real, testable, non-exotic explanation waiting on a specific date in October. A parade of galaxies at the edge of observable time keeps showing up too big, too early, and too structured for the standard model of cosmic history to comfortably explain, with no consensus fix in sight yet. A familiar planet in our own solar system turned out to be quietly cooling by hundreds of degrees for reasons nobody has fully nailed down. And a system of 7 rocky worlds, 40 light-years away, is slowly, transit by transit, giving up hints about whether any of its planets could plausibly hold onto water. None of these stories needed exaggeration to be worth paying attention to. That's really the point. Webb wasn't built to hand humanity neat, tidy answers wrapped up in a single observing run. It was built to look harder and more precisely than anything before it. And every time it does, at least a few of the answers it returns don't match what anyone expected going in. Sometimes that means quietly closing a decade-old mystery, the way the new Tabby's star data might finally do later this year. Sometimes it means opening an entirely new one, the way the impossible galaxies problem keeps expanding with every deep field image. Both outcomes are what real scientific progress actually looks like. Messier and slower than any single dramatic headline, but far more durable, because every claim here is something other scientists can check, challenge, and either confirm or rule out using the same public data anyone can access. That's also why the follow-up dates matter so much. Astronomers aren't just waiting around hoping for lucky breaks. They've already calculated the next windows when a Tabby's star transit could repeat. They've already scheduled more TRAPPIST-1 observing time to settle the atmosphere question, and they're already planning further Neptune observations to track whether that cooling trend continues or reverses. Real uncertainty, in other words, isn't the same thing as not knowing anything. It's knowing exactly what you don't know yet, and knowing precisely how to go check it. If any of these threads get resolved in the coming months, whether that's a confirmed giant companion finally explaining Tabby's star for good, a clearer read on whether TRAPPIST-1e can actually hold water, or a better handle on why Neptune keeps getting colder, that's the kind of update worth actually paying attention to. Not because it's shocking, but because it's true, checkable, and still unfolding in real time. Keep an eye on this space because, unlike a lot of what circulates online about this telescope, every single one of these stories is still being written by actual data, not by guesswork dressed up to look like a discovery. It's also worth saying plainly why real uncertainty like this tends to make for a better story than a manufactured one, even though it's less tidy. A fabricated claim about an alien signal or a hidden megastructure gets to have a clean, satisfying shape because someone invented it to be that way. Real data doesn't work like that. It comes back messy, partial, and full of competing explanations that don't all agree with each other, and scientists have to sit with that discomfort for years, sometimes before anything resolves. The Tabby star story took a full decade to go from an internet sensation about aliens to a specific, testable prediction about a planet-sized object with a name, a mass range, and a calendar date attached to it. The impossible galaxies problem is still sitting in that uncomfortable middle stage right now, with multiple serious explanations on the table and no consensus about which one, if any, is correct. That's not a weakness in the science. It's what honest science actually looks like while it's still in progress, before textbooks get rewritten and before anyone gets to pretend the answer was obvious all along. There's also a quieter thread running through all 4 of these stories that's easy to miss if you're only looking for the biggest headline. How much of this depends on old data being revisited with new tools? The Tabby's star breakthrough came from TESS data, sitting in an archive, waiting for someone to notice a single overlooked transit years after it was recorded. The Neptune cooling trend was first flagged using 2 decades of older ground-based observations before Webb ever confirmed it directly. Even the debate over early massive galaxies keeps circling back to comparisons with Hubble's older observations, used as a baseline to measure just how surprising Webb's new numbers really are. None of these mysteries were solved by one single dramatic image. They were solved, or are being solved, by teams of researchers patiently cross-referencing new instruments against decades of older records, checking and rechecking until a pattern holds up under scrutiny. That's ultimately the difference between a real mystery and an invented one. A real mystery survives contact with more data. It gets sharper, more specific, and more testable the closer scientists look at it, right up until the moment it either gets confirmed or ruled out for good. An invented mystery does the opposite. The closer you look, the blurrier and more unfalsifiable it tends to become, because there was never anything underneath it to begin with. Everything covered here, the tentative planet around Tabby's star, the too massive too early galaxies, Neptune's unexplained chill, and the slow, careful hunt for atmospheres around TRAPPIST-1's rocky worlds, has gotten sharper and more specific with every new observation, not vaguer. That's exactly the kind of mystery worth actually following, and its one Webb is nowhere near finished writing.